Today we are doing our limits review from pre-calculus. So I'm not going to teach it from scratch. I'm assuming that we have already had this once, and this is just going to be kind of a brief review of some of the important ideas of limits. I don't want you to be afraid of limits. They are not difficult. Okay? A limit is the value that the function is approaching, the y value. When I say the function, you think the y value. A limit is what is y approaching as x approaches some number, or infinity or negative infinity. Okay, so if a and l are real numbers, when we say that the limit as x approaches a of f of x is equal to l, that means that as x approaches a from both the left and the right sides of a, the value of the function is approaching L. Y is getting close to L. So the limit from the left is equal to the limit from the right. They are both equal to a number, L. Then we can say that the overall limit is that number. This symbol right here, that means that if this side is true, then this side is true, or if this side is true, then both of these have to be true. So this means it goes either way. This implies this, or this implies that. Okay? Remember that we don't care what the actual point is. All we care is what's being approached, okay? Not equal to. So graphically, have a little graph here. What is the limit of f as x approaches 4? As x approaches 4. So on the left side, we're approaching 2. On the right side, we're approaching 2. So the overall limit is 2. Okay? Nothing too earth-shattering about that one. What this one? X is approaching 2 on the right side of 2. So on the right side of 2. Here's 2. We're going to be looking on the right side of 2. So we are getting extraordinarily close to 2, but not equal to 2. What is the y-coordinate? The y-coordinate is up here, and it is getting closer and closer and closer to 1. This limit is 1. Here we have the limit as x is approaching 2 from the other side. Get a different color here. On the other side. So we're still approaching 2, but now we're approaching it on the left side of 2. So that side. Where's the function? Well, the function is down here. It's approaching negative 1. That's negative 1. So what is the overall limit? If the limit from the right is not equal to the limit from the left, then the overall limit is non-existent. We have an abbreviation for that of DNE. That means does not exist. Or you could write non-existent. Either way. DNE is quick to write though. Alright, what is the limit as x approaches 6? Well, from the left of 6, the y value is getting closer and closer to negative 1. From the right of 6, the y value is getting closer and closer to negative 1. So this limit is negative 1. It does not matter that the actual function value f of 6 is negative 3. F of 6 is negative 3. A limit does not care. We are uninterested in that if we're just doing a limit. We're more interested in that if we're talking about something else, maybe continuity or something else. But for a limit, we don't care about the actual value. Okay, what about the limit as x approaches 8 from the left? 8 from the left is 1. Okay? You would not be asked what is the limit as x approaches 8 from the right, because we have no information about that. Okay? And we're not going to be asked, you will not be asked, what is the overall limit as x is approaching 8, because the other side doesn't even exist. Alrighty? Let's look at this one. New graph, graph of g. What is the limit as x approaches 3 from the left? 3 from the left. Well, here's 3. If we're approaching 3 from the left, what does it appear that the function value is doing? This dotted line, this dashed line, is indicative of a vertical asymptote or horizontal asymptote. Okay, so as x approaches 3 from the left, this function is going to negative infinity. Negative infinity. What about 3 from the right? 3 from the right, this function is getting higher and higher. It's going to infinity. So what is the overall limit? What's the overall limit? The overall limit does not exist. Okay, if even one-sided limit is infinity or negative infinity, then the overall limit does not exist. Even if only one of them is infinity, the overall limit is non-existent. Okay? I probably should have added this one. What is the limit as x approaches infinity of g of x here? As x approaches infinity, what's our best bet here? It looks to me like as x approaches infinity, this is getting closer and closer to 1. Okay? Should have added that in there. I might add it to yours. Alrighty, next page. That's graphical limits. What about if you're not given the graph? What if you're given the equation of a function instead? Here are a list of steps to take if you're just given the equation. Always plug in the x value to your expression. If you get one real number, then you're done. Your limit is that number. Most of the time, though, you're going to get 0 over 0. Okay? When you get 0 over 0, I want you to think chances are there's a hole that you can remove. That is not always the case, but chances are there's a hole you can remove. Okay? So there are 4 things to do if you have 0 over 0. Apply L'Hopital's rule. Okay, when we first began limits in pre-calculus, we didn't teach you L'Hopital's rule from the bat because we needed derivatives for that. But now you know derivatives, some basic derivatives, so L'Hopital's rule is in play, and that is super convenient. Okay. However, if you don't want to use L'Hopital's rule, or it's there's a shorter way to do it, then you can do one of these 3. Factor and reduce, multiply top and bottom by a conjugate, or multiply top and bottom by something to get rid of complex fractions. Okay? To use L'Hopital's rule, I have a box for that down here. To use L'Hopital's rule, there are some conditions that have to be in place. Your numerator and denominator separately. Your numerator and your denominator separately must be continuous. And when you plug in that number for x, you must get either 0 over 0 or infinity over infinity, or negative infinity, whatever. But it has to be either 0 over 0 or infinity over infinity. Those are the only types of functions that you can use L'Hopital's rule on. And if you do get that, then all you do is take the derivative of the top and the derivative of the bottom, and then take the limit of that. same x value, of course. Okay? That's L'Hopital's rule. It only works for 0 over 0 or infinity over infinity. If you do not have 0 over 0 or infinity over infinity, then you cannot use L'Hopital's rule, okay? But you can always, in any limit, you can always factor and reduce. You can always multiply top and bottom by the same thing, okay? All right, if you get infinity over infinity or negative infinity over infinity, yes, you can use L'Hopital's rule, but I don't. I examine where my greater strength of infinity lies, and we'll talk about that in a moment. So the only time I personally use L'Hopital's rule is if I get 0 over 0, okay? If you do not get one distinct number for your answer, then the limit does not exist still, okay? All right, let's do some examples. First of all, number 10 here. When I plug in 5 for x, here, I get 0 over 0. Okay, so we have a choice. L'Hopital's rule, or factor and reduce. It would not be good for this problem to multiply top and bottom by a conjugate, and there are no complex fractions here. So I can either factor and reduce or use L'Hopital's rule. It is easier for me to use L'Hopital's rule, so I will. I keep my limit. In L'Hopital's rule, you must keep your limit. L'Hopital's rule, keep your limit. Okay? Keep your limit. Derivative of the top, put it on top. The derivative of x squared is 2x, little power rule here. Derivative of negative 3x is negative 3. The derivative of negative 10 is 0. The derivative of, and now take the derivative of the bottom and put it on the bottom. So derivative of x cubed is 3x squared. Derivative of negative 125 is 0. You see, I thought it was going to take me longer to do that. Anyway, now we just put in 5 for x. Again, this time when we put in 5 for x, I get 7 on top, and I get 75 on the bottom. This is my limit. Okay? By the way, if we had done the factoring and reducing, if we had factored and reduced, factor the top, it's x minus 5, x plus 2. Factor the bottom. That's a difference of cubes, so it's x minus 5, x squared plus 5x plus 25. The x minus 5's reduced to 1. I plug 5 into the remaining x's, and I get 7 over 25 plus 25 plus 25, 75. So, factoring and reducing works well too there. I think that L'Hopital's rule is just easier. Okay, number 11. When I just plug in negative 1 for x, I get 0 over 0. So once again, L'Hopital's rule or factor and reducing. I don't desire to factor that. So I'm not going to factor that. Instead, I'm going to use L'Hopital's rule. Rewrite your limit. Derivative of the top, put it on top. Derivative of the bottom, put it on the bottom. The derivative of 6x cubed is 18x squared. Derivative of 5x is 5. Derivative of 11 is 0. Derivative of 5x to the fourth is 20x cubed. Derivative of x squared is 2x. Derivative of negative 6 is 0. Now we're going to plug in negative 1 again. Plug in negative 1. I'm going to have 23 in the numerator, negative 1 in here. I'm going to have a negative 22 in the denominator. This limit is negative 23 over 22. Okay, getting a little thunderstorm out there right now. Okie doke. Number 12. Excuse me. I'm at the tail end of a little summer cold. It's kind of a pain. All right, number 12. When I plug in 5 for x, I get 0 over 0. So my choices are L'Hopital's rule, or in this one, I'm not going to factor and reduce. This is a complex fraction. So I can use L'Hopital's rule or multiply top and bottom by something to get rid of complex fractions, right? I'm not going to use L'Hopital's rule on this one, even though we could. I actually might. If it was just me sitting here, I might use L'Hopital's rule. But taking the derivative of negative 1 over x, it's totally doable, but I'd rather review those derivative cases for you. I don't mind doing a little power rule like this. I'm going to wait to review that with you until we do derivatives. So I am going to multiply top and bottom by something to get rid of a complex fraction. So I'm multiplying top and bottom by 5x because 5x will get rid of this 5 and this x. And that's what's making this complex fraction. Whatever you multiply by on top, you must multiply by on the bottom. Okay? You must. Otherwise, you're changing the value. All right, so we're going to rewrite this limit. Okay. 1/5 times 5x is x. Negative 1 over x times 5x is negative 5. So we are left with x minus 5 on top. On the bottom, I'm not going to distribute like I did up on top because that will change. I will just have to turn around and factor it again. So I'm going to leave this in a 5 minus x times 5x on the bottom. Now, these reduce, but they do not reduce to 1. What do they reduce to? They reduce to negative 1. So this limit becomes negative 1 over 5x. Now we put in 5 one last time, and we get negative 1 over 25. Okay? Number 13. When I plug in 4 for x, I get 0 over 0. Okay? So, I could use L'Hopital's rule. Or, I'm not going to factor and reduce. I'm not going to multiply to get rid of a complex fraction because there is no complex fraction. I'm going to multiply top and bottom by a conjugate. Now, we could use L'Hopital's rule here. Okay? But we would have to use the chain rule. We'd have to do some things here because of that square root. So instead, I am going to multiply top and bottom by the same conjugate. So I'm multiplying by the conjugate of this numerator. So I'm keeping my square root of x plus 5. That does not change. But I change the minus to a plus. You do not change the sign under a square root. Only change the sign here. And whatever you multiply by on top, you must multiply by on the bottom. So this limit becomes, okay, square root of x plus 5 times the square root of x plus 5 is x plus 5. The middle term zeroes out. That's because they're conjugates. And then we multiply the negative 3 and the 3, and we get minus 9. Now, what is that? That's just x plus 4, true? I'm sorry, x minus 4, true? Which is this x minus 4 on the bottom. So I'm not going to distribute on the bottom. I'm leaving it x minus 4 times that square root plus 3. Now, the x minus 4 on top and the x minus 4 on the bottom reduce to 1. And this limit is 1 over That's square root plus 3. Now I plug in. Now that I've gotten rid of that x minus 4 that was making it 0 on the bottom, I'm sorry, x minus 4, which was making that 0 on the bottom, I can plug in my 4 again. And I will get 1 over square root of 9 is 3, plus 3 is 6, 1/6. That limit is 1/6. Okay. All right. When you have a limit going to infinity, as x is going, x is going to infinity. X is going to infinity. When x is going to infinity, I want you to think of it this way. I want you to find the highest powered term on top and the highest powered term on the bottom. Highest powered term on top, highest powered term on the bottom. You can ignore everything else. This is the limit as x approaches infinity of just the 4x cubed over the 9x to the 5th. And now your x's reduce, leaving 4 on top and a 9x squared on the bottom. Now plug in your infinity. I'm going to have 4 over 9 times a ginormous number being squared. This limit is 0. Y is approaching 0. It will never reach 0, but it's approaching 0. Okay? Number 15. Again, we have x going to n infinity. This one's going to negative infinity. So I find the highest powered term on top and the highest powered term on the bottom. What's the highest powered term on the bottom? Not 4x squared, the square root of 4x squared. In other words, I'm only ignoring that minus 3. I'm not ignoring the square root. That's part of the function. Some of you were likely taught a little rhyme when you were finding horizontal asymptotes. You were probably taught a little rhyme. The top no, bottom O, same co-rhyme. I don't use that rhyme because it only works if you have a polynomial on top and a polynomial on the bottom. So it would have worked here, but it will not work here, it will not work here, it will not work here. Okay? So I don't want you to learn a rhyme only good for one type of function. I want you to know the process. If you learn the process, you can do it for everything. Okay, so what is the square root of 4x squared? What is the square root of 4x squared? The square root of 4 is 2. What's the square root of x squared? The square root of x squared is not x. It is not x. It is the absolute value of x. Real quickly here, because I do this in class all the time. What is the square root? Oops, why is that so dim? Gosh. Let me try to turn this off. Is that better? No, that's not better. Okay, I don't know why my calculator is so dim. Let me try to brighten it up. Well, that's a little bit better, but still not great. Anyway, okay. X squared. The square root of x squared is the absolute value of x, not x. If it was x, we would see y equals x here, right? That is not the graph of y equals x. It's the graph of y equals the absolute value of x. The square root of x squared is the absolute value of x. Okay, so in other words, the reason I say this is this does not reduce. That does not reduce. Okay? However, they are both of the same magnitude. We're letting x go to negative infinity. So the top is going to go to negative infinity. The bottom piece is going to go to positive infinity because of the absolute values. But they are the same magnitude. So this limit is negative infinity. Oh my gosh, negative 3 over 4. Negative 3 over 4. So, x over the absolute value of x. What does the graph of that look like? X on top, absolute value of x on the bottom. What does the graph of this look like? That's what it looks like. On the right of 0, it's always 1. On the left of 0, it's negative 1. So does this reduce? Well, you could think of it reducing either to 1 or negative 1, depending on where you're at. Okay? So it's either 1 or negative 1. We get the negative. Okay? Number 16. X is going to infinity again, so I need my highest powered term on top and the highest powered term on the bottom. So this is the same as this limit. Okay. Well, we can't reduce at all. This definitely does not reduce. Where is the stronger powered term? Is x squared stronger than e to the x, or is e to the x stronger than x squared as x goes to infinity? That brings us to these infinity strengths. So let's do a quick review. I know we learned this last year. What is the highest powered term that we deal with? X to the x, and versions of x to the x, like x to the x plus 1, and x to the x plus 3, and x to the x minus 2, and all of those. This one is so strong, I have a nickname for him called Big Daddy. That's Big Daddy. Number 2, next in line for infinity strengths, almost as strong as x to the x, x factorial, and versions of x factorial, like 2x factorial and x plus 1 factorial. These are also extraordinarily strong. I call this one Big Mama. Okay? Those are super strong. Next in line, all of our exponentials. So x is in the power, but we have a number as the base. So e to the x, number as the base. 2 to the x, 3 to the x, 5 to the x, 9 to the x. The base has got to be larger than 1. Because if it was 1/2 to the x, it wouldn't even be going to infinity. It would be going to 0. Okay? So the base has to be bigger than 1. I don't have a cutesy name to help you remember that. If you want to make one up, that's fine. I call these the exponentials. Okay? It's not a cutesy name, it's a mathematical name. Okay? Next in line are all of your x is the base and a number is the power. So like x squared, x to the 4th, x to the 7, x to the 1,000, x to the 1/2, x to the 1st. Okay, all of those. All of those come next. I call those my polynomial terms. Okay? One last one, going to infinity, still going to infinity. ln, natural log, or any other base. Any other base. That is the weakest of our infinities, all right? But it is still infinity. These are going to infinity. I call these the logs, right? These are the logs, but I call them, to help you remember them, I like to say that logs are pathetically weak. But they are still infinity, but a pathetically weak infinity. If I type in ln of 99999, a humongous argument, huge argument. Gosh, the thunder was my exclamation mark there. I'm only to 20. That was okay, 1, 2, 3, 4, 5, 6, 7, 8. That was like above 10 billion. Okay? If I do even more nines, well, now I'm all the way up to almost 37. Very, very weak. Very weak. But it is going to infinity. Okay. So here, where's my stronger infinity? Exponentials are stronger than polynomials. So the strength is down here. And since the strength is in the bottom, this whole thing is going to 0. If the strength was on top, the whole thing would be going to infinity. Okay? One more of these. X is going to infinity. So I need my strongest powered term on top and my strongest powered term on the bottom. ln of x is strongest. On the bottom, is either of these going to infinity? Is either of these going to infinity? Well, I know 3 is not going to infinity. Is sine x, does it go to infinity? No, it does not. It does not. This denominator, that denominator oscillates. Sine oscillates between -1 and 1. If I add 3 then, this oscillates between 2 and 4. But the top is going to infinity. So what is this limit going to do? It's going to go to infinity. Okay? So that's how you handle something like that. Alrighty. For one-sided limits, still always plug in the x value first. Ignore the plus or minus first. Just plug in the x value. If you get one real number, you're done. Your answer is that real number. Often on these, you'll get 0 on the bottom only. And if that's the case, your x value is a vertical asymptote. And if your x value is a vertical asymptote and you're doing a one-sided limit, your answer is either going to be infinity or negative infinity. So you need to determine which it is. Okay, and here's verbally what the steps are. I'm going to go ahead and show you from an example. All right. So first of all, I'm going to plug in. I'm ignoring the left notation here and just doing the -7. So I'm going to plug in -7 for all my x's. This is 8, 1 minus -7. 5 minus a -7 is 12. There's a plain x on the bottom, so I have -7 for that. And right here, 7 plus -7 is 0, right? Yeah? So I have 0 on the bottom. 0 on the bottom, and on the bottom only, right? Not on top too. If I had 0 on top too, I would go back. It's like we did before already. So there's a hole, so I'm going to remove the hole. 0 on the bottom means vertical asymptote. So my answer is either infinity or negative infinity. I just need to find out which one. So I'm going to rewrite my limit. I'm going to go ahead and write a number for the top. And on the bottom, I have -7 times 7 plus x. I leave the 7 plus x. I leave the factor that gave me the 0. And now I'm going to ask myself what to plug in. I'm going to plug in something very, very close to -7, but on its left. And on the left of -7 is -7.00000001, right? That is very close to -7, but on the left, okay? And I'm plugging that in for this x right here. If I do that, I have 96 on top, which is positive. I have a -7 on the bottom, and I'm plugging in -7.0001. This, yes, it's going to 0, but it's going to be negative. This is going to be negative, right? So I have a positive divided by a positive, which makes this a positive. Okay, that's how you do those. Alrighty, number 19. We're approaching 0 from the positive side of 0. Okay, first thing I do, I plug in. Up on top, this is just -6, easy peasy. On the bottom, I get 0. 0 on the bottom. 0 on bottom. And not on the top. So we have a vertical asymptote. Yeah? Which means my answer is infinity or -infinity. I just need to find out which one. So in this one, I am going to rewrite my limit again. I'm going to go ahead and put the -6 on top. That stays. On the bottom, I'm going to factor. I want to find out, yes, there's 0 on the bottom, but I'm not sure where it's at, so I'm going to factor this. I can take out a 3x, and I'm left with 3 minus 4x. Now if I put in 0 again, here, here's my 0, and this is 3. So now my limit is -6 on top, 3x times 3 on the bottom. Okay, excuse me. All right, I'm down to my single x here. I'm going to plug in a number just to the right of 0. So like 0.00000001, just to the right of 0. And I'm plugging it into that x. So yes, it's going to be 0, but it's positive. So I have a positive on the bottom, I have a negative on top. So this limit is -infinity. And that's how we do those. Okay, I did write up a nice, easy to follow flow chart for one-sided limits algebraically, and for limits as x is approaching infinity or -infinity. So a little flow chart there if you want to look at that. Otherwise, we're good to go. All right, that's it. Your brief review of limits.